Great. Thank you very much. So thank you very much for the opportunity. I think this is my first time presentation in this ISDA online. And today I heard that this is a special occasion focusing on prediction science. And so I'd like to talk about our activities at RIKEN, that we first proposed this idea of prediction science like 7 years ago or something, several years ago. The RIKEN started doing this research activities about 5 years ago. And so we got some funding from RIKEN to start the actual research on prediction science. So before going into the details, I would like to first thank all those who attended at this ISDA 2024 in October in Kobe. So we had a number of people participating, and we had a very good time to exchange the ideas and also talking to each other. The presentations are available online, so we try to publicize our community activities as much as we can. So please visit again this web page so that you see the program with the links to the talks. Okay. So this is the brief introduction of myself. I will not go a lot of these, but if you would like to know more, I have a web page including this as a front page. So I have been in RIKEN for more than 12 years right now. So, and in the past 5 years, we did the prediction science activities. So this is a web page of our data assimilation research team at RIKEN. This is the most recent picture in October. And we have been working on various problems related to data assimilation using the supercomputers, mainly about numerical weather prediction type of research. So if you think about the technology-driven innovations, what happened in the past 100 years also in weather prediction could be summarized in this single slide. So first we have the weather map analysis that requires the real-time communications of the observed record of pressure, temperature, all those data, and to collect all of these surface station observations for long distance to make the weather map analysis, like pressure contours analysis. That was a major step for the weather prediction. And then in 1950s, we started using the powerful computers based on electric computer devices. So that started the actual numerical weather prediction. And then there are new sensors, particularly the remote sensing sensors, can observe a large amount of the data by these scanning sensors from the radar or satellites. And that initiated these data assimilation and predictability more relevant for weather prediction. And more recently, these are the data-driven type of approach, AI and machine learning, evolving very quickly, so that, for example, recently the global weather model can be replaced by data-driven machine learning. But that requires a lot of data for training, and that data is produced by data assimilation systems using the traditional physically based numerical weather prediction model. But still, a lot of research and possibilities or opportunities for the future development using these AI and machine learning approaches, combining with the existing approaches, and also we start thinking about the control of the weather. So these are a brief summary of what happened in the past about 100 years. And if we think about scientific paradigms, so today my talk has a subtitle. It's a prediction science, the fifth science integrating the inductive and deductive sciences. And what are the inductive and deductive sciences? So first, in my understanding, the science started from observing the phenomena in nature, so that we do the experiments or we just observe the actual phenomena and try to understand what is behind these observed phenomena. So that is based on the data, because we take the data from the nature, and that's known as the first science, experimental science. And the second science is this side, the deductive side. So we understand the process or fundamental rules behind the phenomena, then we can derive equations. And these equations can then, the mathematics could do more than just observations. So the equations can be, well, we can derive new equations based on the existing equations, and that will lead to the new findings or even prediction of new phenomena that was never observed before. That happened, for example, about the existence of Koch's, Einstein's gravity wave. Those were predicted by theory, but was never observed before. But we had new observations recently that suggest the existence of those phenomena predicted by purely theoretically. So these are the deductive type of approach known as the second science. But these are based on the human brain activities. And if we do the computations beyond human capability using the machines, that can also lead to new findings in science. That's known as the third science, computational science. And more recently, we have the data-centric science. It's known as the fourth science. And this is based on the big data analysis beyond the human capability. So these are the four paradigms well discussed so far, and can be categorized into inductive or deductive approaches. So data assimilation combines the computational and also the experimental or the data. So this side and the right side. So that's why I studied data assimilation for many years, and then we came up with this idea of integrating these approaches can lead to something more powerful. So that's the background of this idea of prediction science. And what we have been doing in RIKEN about the data assimilation is to combine the big data with big simulations, because we have the world's leading supercomputers. So we try to explore these extremes, the big ensemble or rapid update cycle, even 30 seconds, or high resolution like 100-meter mesh model for pioneering the future of numerical weather prediction. And that is highlighted by our research on big data simulation, real-time 30-second refresh heavy rain forecast using Fugaku. We did it during Tokyo Olympic and Paralympic Games. And this research was listed as a finalist for the 2023 Gordon Bell Prize for Climate Modeling. So we did the experiment using 1,000 ensemble members, LETKF, and 11 ensemble forecasts for 30 minutes lead time using Fugaku. And we used 7% exclusively. And we ran this type of experiments real time during the Olympic and Paralympic Games in 2021. And we produced this type of prediction at that time. And this is a time series for the whole Olympic and Paralympic period. The left side is Olympic and the right side is Paralympic, and the total about 30 days, like 1 month. And this is a time to solution. So we spend like 2 or 3 minutes to produce 30 minutes lead forecast. And every 30 seconds we run this system. So total like more than 75,000 forecasts were issued only during this 30 days period. It was quite successful. And if we look at some good case of the forecast, so this is our 30 minutes lead forecast, valid 1957, 30 seconds, initialized 30 minutes before this time on this day. And this is the actual radar observation. And we can see that this heavy rain part agrees very well with the observed rain patterns. And the skill is much higher than the persistence. The persistence is the very simple approach, but for this short lead time, persistence is still useful. But the numerical weather prediction, of course, works much better if we can do this data simulation. And because we did every 30-second radar data simulation, we could produce this kind of three-dimensional volume analysis of the radar reflectivity. This is what is produced in the model. So we observe and we assimilate and we produce these rain patterns in the model. So we were motivated to develop that kind of system based on this type of events in Japan, because we have steep mountains, steep slopes in mountains. The water or the rain in the mountains can flow very rapidly to the river, so that this time 5 people were killed by this event in Kobe. It was not flooding event, it's just a rapid rise of the water level, but this can kill people. So we were motivated, and at that time we were very fortunate. At that time, I mean, in 2013, we had a brand new supercomputer K. In 2012, September, and in 2012, August, I think in the summer, we have a brand new phase array weather radar in Osaka. So we were very lucky to have access to these new technologies, and the technologies provide the seeds. So the idea is to combine these two through data simulation. We call it big data simulation because these 2 orders of magnitude bigger data compared with the previous sensors or the computer power. So we combine the radar data. I will skip some of these. And this is the first results that we got. The top left is the observed radar reflectivity, and the top right is what we produced in the model. And the bottom left is what happens if we don't assimilate these every 30-second data. So it's basically impossible to get this observed heavy precipitation in the model without using this radar data. So assimilating this radar data every 30 seconds is very challenging because of the rapid update implies the building up of the instabilities, the imbalances, and that produced lots of strange echoes in the upper troposphere or even stratosphere at the beginning. But we fixed up those problems, and finally we got this stable system. And it took a while, so like 10 years, to make it run in real time. Because the real time means that we need to assimilate the new data available in 30 seconds. Then we need to prepare the background field or the 30-second forecast field and do the DA, the LETKF in this case with 1,000 members in 30 seconds. And at that time in 2021, when the Olympic Games happened, we ran this system real time. Actually, we did it in 2020 with smaller ensemble size, but this was a big ensemble size, and it took like 10 seconds or a little more than 10 seconds, but less than 15 seconds to do the DA cycling computation. So to run the extended forecast for 30 minutes is the most expensive part, and it takes like 2 minutes something. So that's why the total time to solution is about 3 minutes for 30 minutes forecast. So compare with other systems in the world, the JMA operational system, 2-kilometer mesh, and it's similar in other countries. And the update frequency for data assimilation is like 1 hour typically. So it's 120 times more than this 1 hour. So we are thinking what will be the next. So with data assimilation, we could do the OSSI, the observing system simulation experiment, so that we could test virtual observing system that doesn't exist yet, but we are motivated to predict this type of the large scale. The single radar is 60 kilometers range, but this is a larger scale phenomena, so that we would like to have larger area coverage. So we just assume that this network of the phase array radar, now we have like 4 or 5 phase array radars in Japan. So there is nothing like this, but we would like to know how it can help to predict this type of large-scale rain event. And this shows the root mean square error in DBZ. And once we start the cycling, the DBZ, the root mean square error drops rapidly, so that it runs very stably with the 30-second cycle. And this shows the case without radar data assimilation, because if we don't assimilate the radar data, we cannot reduce this root mean square error. But if we do 5 minutes cycling, it can reduce, but it never reached to the level where we get with 30-second cycling. So the 30-second cycling is really effective. So this is a OSSI result. So this is a nature run, and we would like to predict. And this is 1 hour accumulated rain. And without data assimilation, it shifted to the south. So we cannot predict this critical region, heavy rain. The RC result is much better, so that it helps to predict this heavy rain for 1 hour accumulation. And from 1 to 2 hour, 1 hour period accumulation, we still have some skill. If you look at the nature run, there's basically no skill for no DA case. And if you look at the 3 hours or 4 hours, the longer range prediction, we tend to lose the skill because generally the rain system comes from the west to the east, so that it just flows to the east. And we tend to lose the skill if we predict longer, because we have no radar coverage on the western side. So if you look at the skill score, the fraction skill score, this is a single prediction started from 0, 400, and 1 hour, 2 hour, 3 hours. As we saw in the picture, first we have high skill, but the skill drop rapidly like this. In 3 hours, the skill is lost basically. But we can still have high skill at the beginning, and for this type of heavy rain event, this is still useful. And this is very important study to do the value of this type of the data, to test the value of this type of data. Another thing that we explored was radar in space. So the first one was the tropical rainfall measuring mission, the TRIM, and it was launched in 1997. And it lasted for a long time, much beyond the design life. And then it was replaced with this GPM that can go to higher latitude. It's still alive. And what if we had this radar in the geostationary orbit? The advantage of having the radar in geostationary orbit is that we can observe the same spot again and again. So that's essential for the 4-dimensional data simulation for the time series. So we tested the feasibility of this radar system. And this is the simulation of the observation. So this is in nature run, that's the truth. And if you observe this tropical cyclone clouds by that radar from geostationary orbit, because the design of this radar is 30 meters by 30 meters, so that we have a footprint basically the same as these existing ones. So these are the low Earth orbit satellites. So the radar has 2 meters by 2 meters square, and that can have a footprint of about 20 kilometers. So to keep the same footprint size, we need the 30 meters by 30 meters square antenna. So we have 20 kilometers footprint kind of observation resolution. So we lose the details, but we could still see something. But even if we use exactly the same antenna, but if we do the oversampling meaning that the overlapping sampling. So the footprint is 20 kilometers, but we can sample with the overlapping footprint. So that's the oversampling. Then we could effectively increase the resolution of the data. And if you look at the slice, this is the nature run, and this is no oversampling case. We cannot see the details, and the effective resolution is basically the same. But if we do more sampling in space, we could increase the resolution of the data because of more sampling, even though the footprint size is not great. And we found that assimilating this oversampling data improve the rapid intensification of this cyclone. So this is a nature run in 18 hours. So this is 18 hours evolution, and this is a track. The black line is a track. And this red means very high winds. And this tropical cyclone was not as strong as these high winds, the red category high winds, but it evolved rapidly in 18 hours. And we could predict that by assimilating this oversampling reflectivity data. But without using that, this is just a prediction. Without assimilating this radar data, we couldn't really predict this rapid intensification. So this is consistent with other studies like Fuchin Zhang and his group did the airborne Doppler radar data simulation of a hurricane case, and it improved the rapid intensification forecast, intensity forecast. So having the internal range structure in the model could improve this intensity forecast. This is still ongoing research field, so that there is no consensus in the community, I believe, what is the key to the intensification forecast. But this having the rain, precise rain distribution in the inner core part of the tropical cyclone could possibly help improve this intensity forecast. That's consistent. We also explore the big ensemble data simulation. So this shows, this case, the speedy model, simple model, but we run 10,240 members LTKF, and each dot corresponds to complete atmospheric state. And with this, we could investigate the non-Gaussian structure. In this case, the moisture field in the tropical region. There are some occasions where we find this strongly non-Gaussian structure. We can find it with larger ensemble, and we analyze what kind of case we find this non-Gaussian structure. And to deal with the non-Gaussianity, we developed also a local particle filter and Gaussian mixture filter using the existing LTKF code. It's just small modifications made to the existing LTKF code to do this Gaussian mixture particle filter. And that improved the LTKF. So basically beated the LTKF. And particularly if you have this kind of observing network, we tend to have this sparsely observed area having more non-Gaussian structure. We could improve even more in this kind of case. By the way, this white line, because we have a parameter, in this case, the relaxation to prior spread parameter. So this is the inflation parameter. So we need to tune the parameter so that we get a better results. So if we tune the system, we could beat the best tuned LTKF. Okay. So we explore these top science, I would say, using these high performance computers. We now work with Argentina operational service to develop a new system to predict the flood risk in the city areas in Argentina. So the biggest city is Buenos Aires, and we identified a specific river basin. And the second biggest city is, in terms of population, is Cordoba. And we also have Suquía River that is flowing. Well, the Suquía River is in the city of Cordoba, causes flood events sometimes. So we developed the radar data simulation system for these two regions. And this is still ongoing. Another thing we explored was the control of extreme weather events. So we use the word control because it's not just modification, but we try to apply the optimal control theory to the weather system. So data simulation, particularly the ensemble Kalman filter, is based on the Kalman filter approach. The Kalman filter is known as an optimal control method. But the Kalman filter is based on the linear Gaussian theory, but we deal with a chaotic dynamical system. But the characteristic of chaos is the strong sensitivity to the initial conditions or any perturbations in between. So if we have small perturbation, it's very sensitive so that we cannot predict where to go. But we know the range by running the ensemble. And we cannot choose a small difference at the beginning to choose this trajectory. But there is a potential that the small intervention can lead to choosing this desired trajectory. So this is like control of any type of orbit, but the chaotic orbit is sensitive. That's the problem, but that's also an opportunity, so that only small intervention that the humans could possibly make to the atmosphere could lead to a desired situation, like avoiding the heavy rain disaster, something like that. So we tested the idea using this very simple three variable Lorentz system. There is a publication. So we added a very small intervention to this system, and we changed the attractor to be only on the right side of the wing. And we applied the same idea to the Lorentz 96 40 variable system. So this 0 to 40, actually this is from 0 to 39 or 1 to 40, 40 variables. And this is a whole time series, 1 year equivalent time series of 40 variables. And we identify these extreme values, the high values, and twice a year extreme. And this is a histogram of this value from -11 to 17 and 100 years. And we identify this threshold for twice a year extreme high values. And we apply very small intervention only in the local region, and we can see that this histogram change so that we avoid these extremes. Avoiding extremes will be useful if we can make, for example, the tropical cyclone weaker. We apply basically the same approach to these tropical cyclone simulations, and we could reduce the tropical cyclone intensity or the heavy rainfall events. So if you have extreme heavy rainfall, we apply basically the same approach so that we can at least test the idea in the model simulations so that we could reduce this peak intensity and also change the location of the peak area. So this is still a very early stage of the research that we did several years ago. This was presented in EGU 22, and that led to move the Japanese government. So now the cabinet office of the Japanese government decided to start this moonshot research and development program, because this program was started based on our research, partly based on our research that I showed. I was appointed as the program director of this program. So the goal is to, in 2050, we would like to control and modify the extreme winds and rains so that we avoid the disaster. And this idea was highlighted at this IEEE spectrum article, so that now the Japanese government started investing the studies. Potentially we could avoid the heavy rain disaster risk by human interventions like this. Yeah. So these are what we have been doing. In terms of prediction science, so we did data simulation and also the control side of data simulation. But the data simulation combines the inductive meaning we have the data and the data-driven part, and also the deductive, that's more like equations or theory-driven or the process-driven approach. So the data simulation combines these two different approaches. So I thought the broader concept of integrating this inductive and deductive sciences. So if you think about under what kind of conditions data simulation is useful and effective, we need a rich data and a rich model. But even if the model is a little bit poor, or the data has some noise, or the coverage is limited, data simulation can still work. So that's what we have been doing in weather prediction. We have some missing data or some noisy data, but the data simulation includes the noise in the data, so we can do something. And recently, machine learning methods are evolved so that if you have rich data, even if you have no model, or very poor model or no model, it can work. So we can teach this neural network so that the neural network can predict in the case when we can train. So the idea now is how to push this limit towards this direction. So that if you have poor model or poor data, that the data simulation methods even have difficulties, can we really push this boundary towards this direction? So we were thinking what we could do, and now try to explore by cross-disciplinary development. For example, if we think about the red tide prediction, we can use the ocean model with biogeochemical components, but that may not be as accurate, but we may get more data, or we could produce some surrogate model. It may not be directly correspond, but we try to push the limit to beyond what data simulation can do right now. So to do that, we would like to combine the existing ideas. So we work with, for example, the medical scientists for disease prediction, or the climate modeling people for the cloud turbulence model. So we have the limitation of the computational resource, but we would like to do something beyond what we can do at this moment. So to do that, I think already many studies have been done combining the AI machine learning with data simulation, but that's the right direction. So we try to explore what we can do with AI machine learning. So this is our recent paper on the typhoon or storm surge modeling using the machine learning approach. So these are the machine learning models. This is parametric model, standard statistical model. So we could produce this type of storm surge, the wind speed prediction like that. And the numerical weather prediction model works well, and it's really different. So we would like to improve this kind of statistical model. That's a data-driven model. So these are the data-driven model using more recent algorithms of machine learning. Then we can improve quite a lot based compared with this simple parametric model. We also explore the acceleration of the computation of the physical model for tsunami prediction. So this is the tsunami inundation depth, right? Inundation height along the coast. And we could reproduce very well this by using the left side is a physics-based model, and it takes 30 minutes for computation. But we could accelerate the computation like this much, and we can still predict these inundation depths quite well. We also explore the combination of the data-driven type of prediction using the convolutional LSTM with a physically based numerical weather prediction. So this can do merging the two sources to produce the merged AI prediction, so that it can basically produce the best performance. Also, we explore the machine learning approach to the observation operator for satellite radiance data simulation. And we need usually the physically based radiative transfer model, but we try to develop the machine learning radiative transfer model without having any inputs from the physically based models. It's partial success so far, and we try to improve further. So the key is the training data. So we need to have good training data without having the radiative transfer model. And another thing that we explored was to produce a machine learning-based regional weather model. So this is, we can produce the low-resolution global. In this case, we use the Carina, that's existing global surrogate model, and we could produce this type of forecast. But we are interested in the high-resolution true state. By using this high-resolution inputs, we could produce the high-resolution forecast, but that requires the low-resolution forecast inputs, because that provides the boundary condition basically for the regional weather prediction. And so this is a difference, that the high-resolution regional is quite successful in this case, and we would like to do the regional extreme events surrogate model. Okay, I think I'm running short of the time, so I will skip some of these, but this is another study using data simulation to improve the surrogate model. So we use the surrogate model to do the DA, and then we can improve the training data for the surrogate model. So we can do the loop like that until convergence. This is a tropical cyclone intensity forecast using the SHIPS is the statistical hurricane intensity prediction system scheme. And we use the temporal fusion transformer, more recent neural network, and that improved the accuracy. So this is the error metric, so the accuracy quite a bit for in this case 72-hour period, the lead time tropical cyclone intensity forecast. And we also explore other areas. So let me skip this part. Sorry. So this is a collaboration with medical forecast. Basically, we have the record of the disease treatment and medicine, and we just use these data for training and test the predictability. And it seems that we have good predictability based on these actual record of the health records, the medical history, diagnosis, medications, treatments, and that will lead to the optimal treatment. And COVID-19, I will skip, but we also developed a prediction system for COVID-19 and predicted this effective reproduction number based on the limited data. And this is a cell deformation. So the cells change the shape so that those cells will make the shape and the final shape. So the question is how we can estimate the force inside the cell. So we use the Kalman filter to estimate the force inside the cell. So that's how we call this Kalman force inference. And there are traditional approaches that compare with that. This works really, really well. So now we did kind of OSI kind of research, and we could estimate this very well. And I don't show here a comparison with other methods, but compare with other methods. Those are also recent methods. This Kalman filter can work very well to estimate the tension and force inside the cell. Okay, let me skip. We also studied the ocean ecosystem prediction, particularly the red tide prediction, by combining the model simulation, data simulation, and machine learning. So this combination is effective not only in the weather prediction, but also in this type of different applications. So we explored, as I said, in weekend, we have experts in other areas working together so that this project we started about 5 years ago. The weekend prediction science now evolving. And here we also have collaboration with a private company. Now I'm showing the slides from the AGC. That's a glass, it says a glass melting process. So they produce glass. And they have this numerical model for the plant, the glass melting process, and they have very limited data. They would like to do the optimal control of the production process. So the data simulation seems effective. Based on our broad applications of data simulation and the idea of the prediction science in different fields, there are many, many opportunities right now opening up. So this is the final slide showing the concept of this prediction science. So it's really interdisciplinary developments essential for bringing innovations in this kind of integrated type of research. Okay, thank you very much. Sorry for taking a little longer, but I would be happy to take questions.
Thank you, Takemasa.
Yeah.
So, okay, we have one question for you.
Okay, good.
Yeah. So he says, thank you for the interesting presentation. On avoiding extreme events by control, what is actually the modification applied to avoid extremes in the model? Is it mainly to damp the wave when it exceeds a certain amplitude?
That's a good question. We didn't Yeah, that's a very good question. We didn't really analyze what kind of modification could avoid the extremes. But what we found is at least the neighborhood of those extremes, we first need to predict the probability of the extreme event happening. And once we predict where it happens, right? So where it could possibly happen, because we never have the perfect prediction. So we have ensemble prediction, and at least one of, let's say, 10 ensemble members show the extreme value at some point. We don't know if the true value will show that, but we identify the location. And at least if we modify or apply some control inputs to the neighborhood of the location, that is very effective. So we don't need to change the global state. We just need to change the relevant neighborhood. Then that is already effective to avoid the control. And what kind of modifications or the perturbations that we added based on the ensemble prediction? So we have the ensemble common filter, and we have several ensemble members to make the ensemble common filter stable. And then we have the worst case scenario predicted by the ensemble and the best case scenario, the ensemble. We take the difference. Then we basically have one ensemble member going into the direction that we don't want, and one ensemble member that going to the direction that's better. Then if we take the difference, we can push the true system, but we don't know the true system, but still we can push the true system, not going to the wrong, well, the bad direction. So that's what we did. We didn't analyze what kind of perturbations for each case. It's more like a statistical analysis, so that how many times that we can avoid the extremes once the true value shows the extreme. But the assumption that we never know the true value, but we avoid the true value showing the extreme. Make sense?
Yes. Okay. Thank you. Okay, so there's no more questions in the audience, so I think we should probably move on at this point.
Okay.
Thank you very much, Takemasa. Thank you very much.
Thank you.